So let's look at another one of these examples where we're analyzing and sketching a graph. Analyze and sketch the graph of the function f of x is x squared minus 2x plus 4 over x minus 2. So again, we start by talking about the domain. The only value x can't be is 2, so it's negative infinity to 2, and 2 to infinity would be in the domain in interval notation. I find my x-intercepts. I set y equal to 0. Well, that's the same thing as setting the numerator equal to 0. And if you use the quadratic formula here, you'll see that there's no solution. Okay, so there are no x-intercepts. To find our y-intercept, you're going to plug in x equals 0 into your function. If I plug in x equals 0, you'll get 4 over negative 2. So I get the point 0, negative 2. I have one vertical asymptote. It's going to be x equals 2. And then I look for my horizontal asymptote. Well, if I look at either limit of my function, the numerator has larger degree, so this limit's going to be infinity. And if I look at the limit as x goes to negative infinity of x squared minus 2x plus 4 for x minus 2, well, now you just have to look at your, again, your powers. Your degree in the top is larger, and here x squared, look at your largest term, that'll be positive, but x will be negative. Positive over negative, it'll be negative infinity. So here there are no horizontal asymptotes. So now I'm going to take my function and start looking at the derivative. So find f prime of x. You're going to have to use the quotient rule. Low d high minus the top. The derivative of the bottom is 1 all over x minus 2 squared. And if you simplify the stuff in the numerator, FOIL things out, you'll see that the derivative is x times x minus 4 over x minus 2 squared. So if I look for my critical numbers here, I set it equal to 0. I get 0 and 4. These are my critical numbers. So now you're going to find the second derivative of this function, again using the quotient rule, and you're going to simplify everything down. Once you're done, you should get 8 over x minus 2 cubed. So this won't be equal to 0 either, so there are no possible inflection points. So now I'm going to make my sign charts. I'm going to mark my critical numbers, which were 0 and 4. And I'm also going to mark 2 because my function was undefined there. And I just like to write undefined so I don't forget. My function is undefined at 2. This first one will be for the first derivative, the second derivative. So go back to your first derivative. So right here, plug in some test numbers. Plug in, I'll plug in -1, 1, 3, and 5 into your derivative there. So if I plug in -1, the top would be positive, the denominator would be positive, so this would be positive. If you plug in 1, the top would be negative, the bottom would be positive, so negative, negative, and then positive. And then if I look at my second derivative here, again, I'm going to go with those same test points. If I plug in -1, it'll be negative. If I plug in 1, still be negative. 3, positive. 5, positive. So again, what do these mean? For the first derivative, positive means increasing. Here I get decreasing. So here my function and my critical numbers, my function was increasing and then decreasing, so this is a relative max. Here my function was decreasing, then switched to increasing, this is a relative minimum. Okay. So on the second derivative, a minus means concave down. So both of those are concave down. A positive means concave up. All right, so we're going to mark our asymptotes. Let's start there. So the first thing is I had a horizontal asymptote at x equals 2. Now I had no vertical asymptote, but here you do have a slant asymptote. Because the degree of the top is bigger. So to figure out your slant asymptote, you have to divide those polynomials together. So here you multiply by x, and then my remainder will be 4. So my function is really x plus 4 over x minus 2. So this part right here without the fraction gives us our slant asymptote. So our slant asymptote is y equals x. Okay, so let's graph y equals x now. Okay, so here's my slant asymptote. And then I'm going to put on, the only thing I had was a y-intercept. It was 0, -2. All right, so let's see what happens before 0. My graph is increasing and concave down, increasing and concave down, but it's going to want to go to this asymptote, so it should be increasing and concave down. Okay, and then after that it switches to being decreasing, but it's still concave down. Okay. And then you're going to need another point here. So if I plug in, go back to your function, f of x was, what was my function? It was x squared minus 2x plus 4 over x minus 2. And if you plug in 4 into this function, you'll get 16 minus 8 plus 4 over 2. So 12 over 2 is 6. So I get the point 4 comma 6. Okay, 4 comma 6. So after 2, my function is decreasing, but it's concave up. So before here, my function is decreasing, but concave up. So it's going to go up towards this asymptote. And then after that, after 4, my function is gonna be increasing, but concave up still, so it'll look like that. Okay, so if I zoom back out, you can kind of see this is a rough sketch of what the graph would look like for this function.